Hey everybody, welcome back. Mr. G again. Today what we're going to do is a couple of examples for superposition theory. So this is example 1. Really it's the first part. I'm going to kind of explain superposition theory using a couple of numbers, something that we really already know. And then I'll do an actual real example in a circuit, and we'll solve looking for currents flowing through a circuit. In this case, when we have two or more power supplies connected. So what we're going to do is I'm going to just explain or show you superposition theory really simple. So what happens if we have two power supplies connected in series like this, and we have a 1K resistor sitting here, and I'll say that this is 5 volts and 10 volts. Now we know that when you have two batteries sitting like this, they really just add up. So you have power supply 1, we'll call this V1, we'll call this V2. We add those up because they're sitting right beside each other. They produce a current and they have a voltage drop, etc., across a load. So think of this as a flashlight. So this would be the light bulb, and we got two batteries in our flashlight. So we know from real basic circuit theory that V1 and V2, since they're in series, they're just going to add together and we get 15 volts. Now if we wanted to find this I total flowing in the circuit, we would say that I total is equal to 15 volts divided by the resistance of 1K. So that's going to give us 15 milliamps. But now we're going to prove it using superposition theory and prove that this is actually true. So in superposition theory, what you do is you look at each power supply separately. So you look at each power supply separately and then replace the other one with a short circuit. So let's do the 5 volts first. So here's the 5 volts. There's our load. This is where we have removed the other power supply, so the 10 volts, I'm just going to replace it with a short. And then we got 1K. So now we have, if we want to look at the current flowing in that circuit at this moment in time, and we'll call it I1, we could say I1 is equal to, and we have 5 volts divided by 1K equals 5 milliamps. So far so good. So from this power supply, the current that's produced through the load is 5 milliamps. So now what we're going to do is we'll look at it from the other power supply. Which is the 10 volt supply. And now we're replacing the 5 volt with a short. Now we're going to look at this current. This is, we'll call this I2 through the 1K. And that I2 is equal to 10 volts divided by 1K, and that equals 10 milliamps. Now, when we look at I total, so I total is combining I1 and I2. Now, since both of these are going through the load in the same direction, so same direction, we add those currents. So in this example, it is I1 plus I2. So that would be 5 milliamps plus 10 milliamps, which is equal to 15 milliamps. 15 milliamps, 15 milliamps. So When we pop two batteries in to a flashlight, we know the voltages add up and the currents add up. But when we break it down through superposition theory, this is what's actually happening. Okay? So what we're going to do is we're going to apply this now to a real example. So what we're going to do is take a look at a circuit that looks kind of like this. So I've got a 5-volt supply here. I'm going to put some resistors. And what we're going to do is we are going to calculate the value of current through each of those resistors. So we got 4K, we'll call this one 3K, 2K, and 1K. So there's our initial circuit. Two power supplies, 5 volts and 10 volts. So what we're going to do is we are going to analyze two different things. The first thing we have to analyze is the current magnitude being supplied by each power supply. Next is the current direction. So each current's direction as it comes from each supply. So what we're going to do is I'm going to take each circuit or each power supply and remove it one by one and do the calculations and then come back. So we're going to take the 5-volt supply first. So that means that the 10-volt supply is shorted out of the circuit. So what the new circuit looks like would be this. So this is the new circuit. There's where the supply was. So we'll just put a red line there. So that's where we took that supply out of. So there's 5 volts, 1K, 2K, 3K, and 4K. So what we have is a resistance circuit. We have one series component, and that component is in series with these three, which are in parallel with each other. So that whole thing works out to be this. 5 volts, 1K, and this resistor is actually these three in parallel. So these three in parallel, and that works out to be approximately 900 ohms. Okay, so if you put 2K in parallel with 3K in parallel with 4K, it works out to be approximately 900 ohms. So now what we want to do is we want to be able to calculate the total current coming from this supply. So we know that I total, and we'll call this I total 1 is equal to 5 volts divided by, and those two resistors, so that's 1.9K. So 5 divided by 1.9K. So we'll grab our calculator. So 5 divided by 1.9K. 2.63 milliamps. So 2.63 milliamps. So that's the current. So we're going to go back up to this circuit now. So we go from this one, we're going back up to this one. That current leaves the supply. So current going through that 1K is 2.63 milliamps. Then some of it goes here, some of it goes here, and some of it goes here. So now what we're going to use is the current divider formula to figure out how much goes here, how much goes here, and how much goes here of that 2.63 milliamps. So we know that these three things in parallel come out to be approximately 900 ohms. So what we're going to do is we are going to do three simple calculations. So the first one is for the 2K. So we got 2.63 milliamps times, and we'll go 0.9 of a K up top, so that's at 900, and 2K on the bottom. So the current through the 2K is actually equal to that. And if we do our math, so we got 0.9 divided by 2 equals times 2.63 exponent 3 to the negative. So that comes out to be 1.18 milliamps. So that means that this current here is 1.18 milliamps. Now we're just going to apply the same thing, but now instead of for the 2K, it's going to be the 3K on the bottom. So 0.9 over 3K and 2.63 milliamps. And this is I of the 3K. And that works out to be 0.79 milliamps. And then we're going to do the same thing for the 4K. So 0.9 over 4K. So 0.9K over 4K times 2.63 milliamps. And that works out to be approximately 0.59 milliamps. And this is the I of the 4K. So again, go back up to the circuit and add those numbers in. So for the 3K, it was 0.79 milliamps. For the 4K, it was 0.59 milliamps. So 0.59 milliamps. So the current through the 1K is 2.63 milliamps, and it's going this direction. Through the 2K, it's 1.18 milliamps going that direction. Through the 3K, it's 0.79 milliamps going that direction, and through the 4K, it's 0.59 milliamps going that direction. So that's all the stuff that we need to know for the 5-volt supply. So now what we're going to do is we're going to create the next circuit for the 10-volt supply and do the same thing. So the 10-volt supply, again, we're going to short out the 5-volt and just go with the 10-volt. So the 10-volt supply looks like this. So this is the 4K. That's the 3K. Here's the 2K. The 1K. And again, I'll just make a red line here. This is where we removed the 5-volt supply. So now this is 10 volts. So now what we're going to do is we're going to do the exact same thing. Okay, we're going to look at this circuit. We've got this resistor, which is going to be in series with these three in parallel. So that works out to be a circuit that looks like this. Where this is the 4K, and this represents these three resistors, and those three resistors are going to be in parallel. So when I do that mathematical thing, it comes out to be 0.54K. So those, a 1K, a 2K, a 3K in parallel comes out to be 0.54K. So now, I'm just going to try and make a little line here. So now what we're going to do is we're going to find our total current. So our total current, and we'll call it current total 2, is 10 volts over 4.54K, and that works out to be 2.2 milliamps, Ohm's law. So now we're going to then go back up to this circuit and break things down. So the total current leaves the source, goes through this resistor in this direction, and it is 2.2 milliamps. Then some of it goes this way, some of it goes this way, and some of it goes this way. So how much goes through each? We're going to do the voltage divider thing again, or sorry, the current divider thing again. And we're going to figure out that we've got on the 3K, so it's 0.54K over 3K times the total current, which is 2.2 milliamps. And that becomes I of the 3K. Then we got I of the 2K, and we have I of the 1K. So that becomes 2.2 milliamps, 0.54 over 2K, 0.54 over 1K, 2.2 milliamps. And if we do that math, let's see, this one works out to be 0.396 milliamps. This one works out to be 0.594 milliamps, and this one works out to be 1.18 milliamps. So now we're going to plug those magnitudes up into the circuit. So this one here is 0.396. This one here is 0.594. Sorry, 0.594. And this one is 1.18 milliamps. So now, what we have is we have our magnitude and direction from this supply, and magnitude and directions from this supply. So the rule of thumb is if the currents are going through in the same direction, they get added. If they're going through in opposite directions, they're subtracted. So we're going to take both of those things and superimpose them onto the original circuit. So we have this way 2.63 milliamps. From this supply, it's going this way at 1.18 milliamps. So this power supply puts 2.63 milliamps going that way through that resistor. This power supply puts 1.18 milliamps going that way through that power supply, or through that resistor. This power supply here is putting current this way at 0.594, so 0.594 milliamps. This power supply is putting current this way at 1.18 milliamps. This power supply here is going this way at 0.79 milliamps, and this one is going this way at 0.396 milliamps. This one puts current going this way at 2.2 milliamps. This one puts current going this way at 0.59 milliamps. So now what we need to do is we need to do our math. So when we look at the current, so we're going to say the current through the 1K resistor, it is 2.63 milliamps. And since they're going in opposite directions, minus 1.18 milliamps. So we have a magnitude here of 2.63 3 minus 1.18, 1.45 milliamps. 1.45 milliamps. So through the 1K. Which one is the dominant? This one. So that means that this current will be flowing that way through the circuit. So let's take our circuit, we'll duplicate it right here as the final. So we've got 5 volts, we've got 2K, we have 1K. This was the 10 volt supply. This is the 4K. This is the 3K. 2, 1. So now what we've done is we have calculated the current 1.45 milliamps. So the current through this resistor is 1.45 milliamps, and it's flowing in that direction. Let's do the 2K. So the current through the 2K is equal to, what do we got? 0.594 milliamps. And because the other current is going through in the same direction, plus 1.18 milliamps. So 1.18 milliamps plus 0.594 milliamps. So this current is 1.77 milliamps. So the magnitude is 1.77 milliamps, and the direction is this way. Let's look at the 3K. So I of the 3K. So in the 3K we have 0.396 milliamps, and the other current is going in the same direction, so that's 0.79 milliamps. So we're going to add those up. So 0.79 plus 0.396, 1.186 milliamps. So again, since both of them are going in this direction, they are added together and they get 1.186 milliamps. So last but not least, we've got the 4K. So current in the 4K resistor. So we have 2.2 milliamps. And the other current's going in the opposite direction, so that was 0.59 milliamps. So the magnitude here is 2.2 minus 0.59. 0.59. Oops. 2.2 minus 0.59. There we go. 1.61 milliamps. 1.61 milliamps. So the magnitude here is 1.61 milliamps, and the direction, so we had a larger one going this way, so that means that the direction is here. So starting from the original, we work out one supply, work out the second supply, and then superimpose them back onto the original circuit with the math. Again, you have to remember there are two parts to each one of these. One is the magnitude of the current. The second is the direction. So the larger current, if the two are going in opposite directions, the larger current determines the overall direction. So in this case, we had 2.63 going that way and 1.18 going that way, which results in 1.45 going that way. It's the algebraic sum, so taking into account direction. So This is superposition theory. You can find superposition theory in your textbook. So chapter 8 and superposition theory is, what do we got? In our textbook, superposition theory 8-4. So section or chapter 8-4 of the textbook for more examples. There is also a theorem procedure that I put onto your Blackboard site under your lesson notes. So this is example number 1. I'll be creating another video with example number 2 and posting that as well so that you have a couple of different examples to look at. Well, I hope this helps. Our textbook, Principles of Electric Circuits, Conventional Current Flow by Floyd and Buckla. Everybody take care, and we'll see you again next time.